Swayam Prabha. Digital India. Educated India.
Begin by thanking the organizers for giving me this opportunity. Come to this great conference and present just something of what we have been doing in the last several decades. Now, what is more exciting for me to come to this meeting has been that it is organized for celebrating the 75 years of Sati. Sati has been a good friend. I think we met first maybe 44, 43 years ago in IIT Kanpur, and we have worked together on many different organizations, though we never published anything in scientific research, but we had long interaction, not in one place but across institutions in the country. And what is more interesting is that about 20 years ago and about 100 kilometers from here we had met, and that was this is a photograph from that occasion. This is when Professor M.S. Gopinathan was retiring from IIT Madras, and they had an evening that was there about 100 kilometers from here towards Chennai. Now, I would like to say, I wish, of course, Professor Sebastian was also here, but he was not traveling. Sadi has been constant in the way he looked, and it was very nice because, age is just a number. Sadi doesn't change with it, and I wish you the very best for so many years to come. It is really very nice to see all of your friends also here, wishing you the very best in life for many years to come. So now I come to just one topic I have selected because the research that I do often is in specialized chemistry areas, and most people are not so very keen to say whether it is a transition metal catalysis or a main group structural analysis or things like that. But one topic that is common is about the elements of the periodic table. So I tend to talk about that all the time, and I talk about the fifth element, and the title actually came to me because I was talking to lots of people who are not in chemistry, who are not even in science, and so they say, okay, there is the fifth element, and for many of them it is not an element of the periodic table, and for some of them, and I say that there is another element, carbon, which is the sixth element in the periodic table, and they say, oh, well, sixth and element is not the word that comes to many people, it is the sixth sense. Now, what I would like to tell you is that the fifth element here is actually from the periodic table, and that fifth element is boron that I would like to talk about. And why boron, I would leave that because boron has so many applications. And why the sixth sense? Because I was trying to understand the structure of elemental boron, and I couldn't understand anything for a long time. And it appeared as though one needs a sixth sense, and that sixth sense is also right here, the sixth element. So this is the reason I gave the title. Now, this is a general picture that I would like to begin with. This is the structural chemistry of carbon as we know it. We have diamond. The tetrahedral carbon came already in 1874. We had, even before that, trigonal planar carbon came in 1857. Kekulé had the structure. We had the diamond structure established by Bragg in 1913. 1914, the graphite structure was established. And 1936, we had the Huckel rule, benzene, naphthalene, and further on. In 84, I'm jumping in, suddenly we had another allotrope, fullerenes, C60. In 87, IGNOU has the carbon nanotube, which is also, quite interesting. They were all landmarks in these. And of course, 2004, a layer of graphene is taken out of graphite, and we had a lot of chemistry that is going on in the last 20 years. This is a general picture of the structural chemistry of carbon. Now, if you have an undergraduate student coming in who is not able to understand this, who already did not know this knowledge, we would find it very abnormal, right? Especially if a graduate student comes in after BSc and BSc in chemistry and this information is not available, it will be considered very abnormal, right? What I would like to say is that if we get even another allotrope, like what happened this year earlier, C48 as a carbine chain, you can ignore these hanging other molecules. But even the C48 is understandable. It just is slight deviation from the linear structure. So we have another allotrope. And I suppose that we can think of other allotropes as well, many more. But there is a general feeling that we have this knowledge of structural chemistry. But if you want to ask the same question, what is the structural chemistry of boron, the next element? How many of us can say that, okay, I also have a general idea of elemental boron structure, right? And that's what I would like to come at or try to explain today. And this leads me to the pictorial presentation of what I'm going to talk about. So this, according to me, will be the equivalent of the carbon picture I showed in the slide before. Now, what is this picture? This picture talks about polyhedral boranes in the middle. It's called the Rudolph diagram. B12, H12, 2 minus, and Nido and Arachno. And of course, B12, H12, 2 minus, you can go all the way to B4, H4, which is of course neutral. So this is the Rudolph diagram that is there in textbooks. And I would like to say that we have to extend this to get 3-membered rings, and from those 3-membered rings we can generate flat structures, and those flat structures will be borophenes. And perhaps with time we will have borophenes put together. We can have a bilayer borophene. We can stack infinitely, perhaps even to go to borophyte. These are things that possible. We can possibly connect polyhedral boranes, especially B12, to the 3D allotropes. And this general picture is what I would like to explain. So this would be the equivalent of the carbon structural chemistry for boron. I don't know whether this could be called a theoretical chemistry, I'm not sure, but this is indeed chemistry for sure, because the earlier picture that we had of carbon was chemistry, and that was not considered theoretical chemistry alone. It was a mixture of everything. So we are developing something similar. Now you can ask why I'm worried about this, how did I get there? I had a very good teacher in my first year BSc who was talking very elegantly about this. At that time we had graphite and diamond, and he finished this particular topic. It was an organic chemistry course, Professor Shankarayar. He was walking away, and I said, look, is there something like this boron? Without thinking much about it, I asked him this question. He was a good teacher. We looked around. I asked, is there something like this for boron? And he said, let us look at it. We had 1964 edition of Cotton and Wilkinson, and there was not much that we could get. Then went on to do a MSc at IIT Kanpur, and I had a great teacher of inorganic chemistry, Professor P.T. Manoharan, at that time in IIT Kanpur. And the same question was asked, and he said, well, not very clear, but in this course you can write an essay on many topics. He gave 20 topics, and one of them was on metalloboranes, and I selected that one. But I kept going, and I went to do PhD, and I told my supervisor that, look, I would like to work on this. This problem has been there in my mind for long. And he said this. This is a typical way. He said, well, you work on lithium compounds, and that's my interest. And so I kept that on, but you keep going, and I am at this stage wanting to do things. It is good to have one's own question as much as possible. But 2 years after I joined, well, almost 3 years, there was a Nobel Prize announced, and it looked very attractive to look at this Rudolph diagram again, and there is even a Nobel Prize attached. But my professor was clear that, look, you have started with the lithium, now you look at organolithium compounds and planar tetracoordinate carbon and many other things. So I didn't get into this in my PhD time, but there was something interesting about the thesis submission at Princeton. I had to submit a PhD thesis, but there was no need to defend it. But along with the PhD thesis, I had to give research proposals, 3 research proposals which are not connected with the thesis and which are not even connected with the research area of your supervisor. So we had to give 3 such research proposals, and of course one of them was boron for me, especially polyhedral boranes. At that stage I hadn't reached to the elemental boron stage. These research proposals are one's own proposals. It is not of your research supervisor. So I kept it on, joined University of Hyderabad, didn't have any students, but I worked on the first of them, and that was on polyhedral molecule stabilities. For example, this paper described how perhaps we could have 14 vertex systems which would be more stable, how the carborane relative stabilities could be explained, and so on. Got a PhD student, we worked together to see how one can explain why boron alone has icosahedral structures as the most stable one and not other things. So we had this unusual possibility that B12, H12 among all the other polyhedral boranes is the most stable one. There is an explanation published in Proceedings of the Indian Academy of Sciences, which eventually became Journal of Chemical Science. Now, while this was going on, something else happened. 84, there was C60. And the C60 was fascinating because I was looking at elemental boron structure that is available, beta rhombohedral boron. A rough structure was available in the late 50s, and that has something something looks very, very similar. One of the building blocks of the elemental boron, beta rhombohedral boron allotrope, had almost the structure of C60. It's actually B60, and below every 5-membered ring in this B60, there is another atom, and there are 12 such 5-membered rings in C60. So there are 12 such atoms, and those 12 atoms are connected to a central B12. So we actually have B60 plus 12 atoms plus another 12 atoms. So this is B84. That is one of the building blocks of beta rhombohedral boron, right? Now this building block, if one put together more carefully, just looking at the known structure at that time with the details, it's as if, I'll explain this once again. B12, starting now from the inside structure, a pentagonal pyramid is added. 6 of them are added. Here the 12 of them are added, and that's where the B84 came in. The actual structure has 3 of these B84s connected to a beaten unit. So you have this arrangement, a beaten in the middle, and this beaten is unusual because it has a central boron atom and a 5-membered ring here, another 5-membered ring at this point, a third 5-membered ring. That means if I connect this pentagonal pyramid with the top of the B84, we have a pentagonal pyramid from this end, another pentagonal pyramid from that side, and we have a B12. So essentially the attempt is to have maximum B12s. B12 is the best structure for boron. The problem is that I thought I can understand this, but you reach up to this point, the structure is not over yet. Something that is connecting this to another equivalent structure is the beta rhombohedral boron structure. It was not known exactly by that time, but by 1988 it was known. But I couldn't understand it yet. I thought it will be easy to look at something like this, benzene, naphthalene, anthracene, Huckel-Farren +2 rule, and we should have some rule to put them together. I tried this this is late 80s and didn't succeed, so I left it. Went on further. When you are in academics and you have a problem and it's not working and you say, I will keep working on it even if it is not solved, then you will be thrown out of the job. So I had to keep doing things, something else. So I did work on many different projects and topics as varying as these. And each of them are equally interesting topics. I would in a chemistry conference I talk about this, but in the chemistry conference of this kind, theoreticians come, I don't talk about these largely experimental problems. Then I thought, if I didn't succeed in this, is there anything wrong? See, I looked at carbon chemistry again. It's always 6-membered rings: benzene, naphthalene, anthracene, decalene, and diamondane, and finally diamondane, going all the way to diamond. 6-membered ring seems to be the rule. And I thought, if you have to go to an element that is having 1 electron less, and still one has to think of aromaticity, then maybe we should go to cyclopropenyl cation and its equivalent. Like these, we have B3H5 neutral 2pi system, B3H6 plus, and so on. So we studied that, and it was interesting because we found that the B3H5 is an aromatic system, but B3H6 plus tend to be non-planar, and we can easily see why it is non-planar, because the plus combination of the 3 bridging hydrogens can only interact with the pi system if it is out of the plane, and that's why it is non-planar. Nothing very unusual. This is just an explanation of this. So I was looking at this older picture and I thought, okay, this is 92, 93, 94. I thought, instead of 6-membered rings and instead of B12, how about starting with the 3-membered rings and see if it is possible? Like B3H5, can we do this? And I couldn't really, understand it well enough at that time, so didn't publish anything. B3H6 plus also we thought not quite reaching there in 92, 93, 94, and I left it at that stage, unfortunately. Then I got a good postdoc who said, okay, let us go back to your earlier problem and look at this. And he felt that if one were to look at literature, probably there is this B20H16 that is already known, and we could have an equivalent of a 3-dimensional Huckel 4n plus 2 pi electron rule. And that I thought was a successful one. We called it as n plus m rule, because m is a variable that is added to indicate that there are more than one polyhedra. Huckel didn't have that problem. With that, I thought, okay, we can now go to this. Unfortunately, no, because what happened is that this unit connected to another one through a single boron atom was one of the structural aspect of beta rhombohedral boron. The unit cell is idealized unit cell is 105 atoms. So we went back to the earlier picture and thought, okay, something more to be done. And so we changed this rule to have one more variable where if the polyhedra are connected through single atoms, then the single atom uses orbitals on both sides, so to speak. So we need to have an extra pair of electrons added. So this was helpful, and then we could explain the beta rhombohedral boron structure easily. Now I'm not going to talk about the beta rhombohedral boron because it is there in textbooks, but we could do this part of it. That is, Closio B12H2 minus can be connected to both beta rhombohedral boron and tau boron. Tau boron didn't exist at that time. It came in 2017. Beta boron, the detailed structure came in 1988. There are textbooks that describe this now in great detail, so I wouldn't spend any time on this. But in 2001, something else happened. Akimitsu measured the conductivity of magnesium boride and found that at 40 degree Kelvin, this is superconducting. Suddenly it was a dramatic discovery, because a few years before that, for 22 degree Kelvin material, which is very complex, a Nobel Prize was given. So this is MgB2 binary structure, having a conductivity, superconducting behavior starting at 40 degree Kelvin. We thought we will look at this and see whether from this we can go to boron structures, taking away the metal. We are talking about, at that time already in 2004, something else had happened. One graphene was taken out. 2001 was the time when magnesium boride was found to be superconducting. Now, all of these gave some confidence that we should look at this old problem again with remembered rings to 2 dimensions. And I got a student, Prasad, who said, let us look at all of these things as though it is like graphene. He called it borograph. We were talking about graphite and we are putting boron instead of calling it borofene these days. Now, his thesis actually presents the idea that if it is a flat borofene kind of sheet, graphene kind of sheet, it will have triangles and some holes. But before we published it, there was another article that has come, computational work, which said that this is not the most stable arrangement. It is not flat. It will be having ups and downs of these atoms if it is a triangular structure. And if you remove some holes, it will be even more stable. And I thought this is the time to continue with this work, but something happened. There's a blank slide here. This blank slide stayed on for my boron chemistry for next 5 years, because I had to leave for starting another institute, and we had this campus. And I got back in 2013 and thought that, okay, at least now we should be able to come back to this if it is not done. It so happened that large number of computational results were there on borofenes, but none of them could understand why there should be some holes. And we started with this idea that if it is MgB2, right, aromatic structure anyway, if it is MgB2, it is good. So how about getting borofene out of it? We replace an Mg by a boron. If you replace an Mg by a boron, all are boron. It is not alternating layers of boron, magnesium. So when the boron falls down from the top, we have no holes anymore, no hexagonal holes anymore. It is all boron, only triangles left. The only problem is that when we replace an Mg by a boron, we have an additional electron. If you want to go back to the same electron count as graphene, we have to remove then electrons. How do we remove electrons? Electrons can be removed, like if you are considering a stoichiometry of 3 times. By this time we have 3 borons replacing 3 Mg. So we have 3 electrons to be removed. One way of removing the 3 electrons is to remove 1 boron atom out of 9. If you remove 1 boron atom out of 9, then we have the same kind of a structure like graphene. We published this, and then we thought, okay, if this is interesting, maybe we should go further to many other things. And that is, well, when this work was going on, suddenly it shocked us. We wanted to have this for long, but in 2015, first of these borofenes were made. More experiments are coming in. I will skip this. These are not as important. While this was going on, we felt maybe there should be ways in which one can make borofene without any holes. And one possibility we thought was that we should take a bilayer. We know about graphene bilayers. Graphene bilayers, depending on the angle between the layer, we could even have superconductivity. But then it is weak interactions between the 2 layers. But if you take borofene bilayer, one finds something very interesting. This is bilayer without any holes. Find that they are not flat, but if you have 2 of them, 2 layers, then we could think of a hexagonal pyramid coming from the top layer, another hexagonal pyramid from this, the boron atoms coming out of the plane, and they can form a 2-center 2-electron bond. Now, if they form a 2-center 2-electron bond, 2 electrons are removed from the delocalization. And if you have removed 2 electrons from the delocalization picture, it is equivalent of making a hole. And if you have 3 such bonds for every 9 boron atom of one ring, we have achieved the same thing as having one hole, right? And of course, I mean, these are computations and speculations. We were initially very skeptical to publish it, but we published it. But in 2 years' time, not 2 years, 4 years' time, 2 years ago, 3 years ago, there were 2 papers where they have made the bilayer borofene on a silver 111 surface. And this was interesting in many ways because this gave us more confidence to look at these models again. See, for example, how about a tri-layer? See, this is a very schematic way of showing that this is a bilayer. For every 9 boron atoms, there will be 3 bonds. If you take a tri-layer, right? If you take a tri-layer, in the middle layer has 9 boron, 3 bonds for every 9 boron atom, but the top one has only half of that, which means that here we should have a hole for 18 boron atoms, not 9, right? And we have published this. We are sure that it's only a question of time that somebody will make the tri-layer as well. Now it is trivial to think about tri-layer, tetra-layer, penta-layer. All that we have to see is that the top and bottom layers will have 1/18 hole density. The middle layers doesn't have to have any holes. Now this picture is really the beginning point that, okay, if that is the case, how about thinking of a borophyte like graphite, right? We can take a bilayer and make a borophyte because this is electron sufficient one. We can take a tri-layer and make a borophyte, right? Of course, this is where work is still going on because we find that this idealized one, when you do molecular dynamics at higher temperatures, of course, it will fall apart. That temperature changes depending on what is the nature of the layer that we have, right? So this is something interesting. It's a work that tells us that one can speculate, and there will be some possibility that if it is reasonable, it will be made. Because bilayer, the experimental formation of bilayer gave us more confidence in this. Now the proposal comes back to 3-membered rings. If you have B3H6 plus, I said it is non-planar but 2pi aromatic. If you consider this bridging hydrogens and replace each of them by boron and the right angle, we can have either octahedron or all the other polyhedral structures which is there. But how do we get a 3-membered rings into this picture? And that's where the B4H4, that was the last one in the Rudolph diagram, comes in. If you consider the Rudolph diagram, and if you consider the Rudolph diagram, and if you get to the structure like this, right, we can go through all of the standard variations that I mentioned about. So from here, we generate all of the Rudolph diagram. From the borofene point of view, it would be B3H5. If you start replacing the bridging hydrogens by other BH groups, you can get all the way. And on this side, there is a hole that is always there, so that we have the hole density also coming in exactly. So this is the way in which I have thought of giving the picture. Of course, it is not the end of the picture, because even after 150 years, we are having more structures from the carbon family. Boron family will continue. But what lies ahead? A lot. We have MgB2, we have MgB4, we have MgB6, we have the possibility to use our rule for Zindel ions and many other areas. So there is plenty of work to continue in this. But let me thank Professor Ashwini, Sanjay, and Raj for inviting me. And I don't have a big group. These are all summer participants and visitors from the previous years of my own group. So I will stop at this stage, and thank you for your kind attention.
Swayam Prabha, Digital India. Educated India.